So my name is Lisa Giroux. I'm a practicing professional engineer, work with Hazen and Sawyer. We're an environmental engineering company. We design predominantly water structures, wastewater structures, dams, water control structures, that type of thing. So for us, cracks are pretty important. Wanted to take a look, I wasn't in the first session this morning. How many contractors do we have? So few. What about engineers? Ooh. Producers? About the same number of contractors, and any owners present? One. So mostly engineers in this particular audience. Well, the Cliff Notes version is crack-free is a misnomer. We design concrete knowing that it cracks. So, the question that I have to ask is, if we design it knowing that it cracks, why is there such division among the stakeholders when the cracking occurs? Why is that such a problem? If parties know that it cracks, why is that an issue? Because the cracks, different reasons, but cracks can be aesthetically undesirable. We can have maintenance and durability issues that are created because of the cracks. Rather than crack-free, I think what we've talked about earlier in the presentation is crack control. That's a focus, to be able to manage the cracking that we get. So rather than crack-free, I think that's what the conversation should be about from an engineering and design perspective. And if we are looking at crack control, that begs the question, who's responsible for the crack control? And in my opinion, everybody plays a role in the responsibility. Owners need to have realistic expectations. They need to clearly establish their goals so that the engineer and the contractor understand those. Engineers have a planning, design, and specification responsibility in order to specify the concrete to best achieve those goals relative to the layout and the design required. And contractors and producers have a construction responsibility to mix and place the concrete to help achieve all of the goals. So to me, it's a shared responsibility, and communication is critical to achieving the desired results at the end of the day. These are the type of structures that I typically design. One, for durability is a key requirement. In fact, in 350, we consider it a limit state. Our structures contain, treat, transmit liquids. We need the concrete to be liquid tight or gas tight, and we need it to function under service conditions, which are generally fairly high, with minimal leakage. Our concrete can also be subjected to aggressive environments. The concrete here was about 10 years old when this deterioration was discovered. There was biogenic corrosion that had eaten through the concrete protective coating that had been installed on the concrete and had started in on the concrete matrix itself. The section loss here was around 4 to 6 inches, not exactly what you'd be expecting to see if you're an owner and your concrete is only 10 years old. Our loads can be pretty significant. There's about 4 stories of water behind this concrete dam, so that is no small change in terms of pressures. So if we're looking to focus on crack control and design for that, we need to make sure that we've specified the concrete mixture with that goal in mind, that we design the members for strength, and that we've provided the reinforcing necessary, including the minimum temperature and shrinkage reinforcing. We want to make sure that we've located the joints, either through hard locations on the drawings or specifying maximum restrictions for the contractor's means and methods to place and cure. We also want to make sure that we are focusing on placing and curing properly so that the concrete can achieve what we want it to have at the end of the day. So from our perspective, we want to look at designing the concrete for the loads that we're going to be under. Our focus is strength, safety, with the knowledge that the concrete will crack. We also need to make sure that we specify the concrete for the environment that it's going to be in. These are the exposure categories from 318. 350 exposure categories I'll have up in a minute. This is a part of trying to make sure that you maintain the durability or the serviceability of your structures. Our 350 tables are a little bit more in depth because some of our exposures are more restrictive than what typical building structures would have. So those exposures are going to make you look at required strength, minimizing shrinkage, typical exposure conditions for your freeze-thaw, sulfate contact, water contact, corrosion of your reinforcement. For environmental structures, erosion and chemical attack are also exposures that we typically deal with that wouldn't be present for a general building structure. For freezing and thawing, sulfate, the table on the left and right are the 350 exposure categories. Just go through these real quick. Our corrosion of reinforcement and protection against chemical attack are tables for 350 for those, and for erosion protection, these are the tables for erosion. And I'm sure you could think back to the dam that I showed with 4 stories of water and imagine the velocities that water will display when it's going down the face of the dam and the erosion that you could get from that. Looking at just a brief example, we have a process tank that's here in Deer Island, which is due east of Logan International. We would have a freeze-thaw durability, a freeze-thaw exposure category of UF2. We have freezing and thawing temperatures here in this area, and sulfate. This is a wastewater structure, so it would have a sulfate exposure of ES2. EC, our corrosion reinforcing exposure category, we'll say it's an EC2 due to the potential source of chlorides that are present from our coastal environment, as well as we have the potential for chlorides often in the treated water. Our chemical attack, we'll say, is an EC1 for this particular example, that we're not expecting chemicals that are going to corrode the concrete beyond at a faster rate. We're looking at a slower rate of corrosion. And then for this particular structure, velocities are lower, and we would have an erosion class of E0. So you go through the tables, and as you go through each of your exposure categories, you would kind of go across, get your compressive strength requirements, your minimum compressive strength, your maximum water cementitious materials requirements, and in some cases there may be additional requirements relative to cement type or air or pozzolans, depending on what the exposure requirements are. You're going to go through those for each of the exposure classes. You should also consider ASR, the potential for ASR for our type structures. We're often assuming a risk level 3 with an aggregate reactivity level R1. Water and wastewater structures would have a structure class of SC4, which would give us a prevention level Y with a requirement of 3 pounds per yard for maximum alkaline loading for those givens. So you put all of that kind of in a table and compare what you end up needing, and when you look at your controlling compressive strength and your controlling water cementitious materials ratio, we would find we would need a 5,000 psi concrete with a maximum water cement ratio of 0.4. For this particular example, we would also need to look at type 5 cements or type HS 595 cements. We also have maximum chloride restrictions, air entrainment requirements, and pozzolans would be recommended to help control aggregate expansions. I've not included on the slide some additional pozzolan restrictions relative to maximum and minimums, depending on your freeze-thaw. That is just a little bit more than what we were going to. You also want to make sure that you have reinforcing design for the temperature and shrinkage stresses that would be experienced during placement. If concrete is placed and it's free to deform, then it just shrinks and you would experience no stress. But the reality is, after you place the concrete, it's going to be restrained by other elements, beams, columns, walls. There will be something else that restrains it, and when that happens, you're going to get tensile stresses that develop in the concrete. And when the concrete cracks, it is relieving those stresses. Your compressive strength is much greater than the tensile strength. Tensile strength is only about 10 to 15% of the compressive strength, and cracking starts when you reach that tensile strength of concrete. Unless your reinforcing unless you gain enough strength concrete-wise to where your reinforcing can be effective, then you're going to see the cracks develop. So we want minimum temperature and shrinkage reinforcing to tie the structure together. Yes, that's 318's goal for providing minimum temperature and shrinkage reinforcing. For environmental structures, we also want to minimize the excess cracking that can occur. That temperature and shrinkage reinforcing is perpendicular to the primary reinforcement. This is an example here of restraint-induced cracking, where the cracking is present down at the base of the wall, but dissipates as you move up the wall, and that's a situation where the base slab for the tank has restrained the wall as the wall wanted to move after its place. And restraint-induced cracking is something that needs to be considered in the design. One of the most important tools for minimizing cracking is joints. Joints allow for movement. They provide a construction convenience. That's not their only reason for breaking pores. That's not the only reason to use them. They help manage stress and minimize cracking. All of the joints should be shown or indicated on construction drawings, construction documents, be it either specifications or drawings, whether they're hard located on the drawings or whether they're specified at maximum distances. Just an example here. I typically like to locate joints where the aspect ratio is around 0.75 to 1 to help control and distribute. Our goal is to get many fine cracks rather than fewer wider cracks, so that for our type structures there's less potential for leakage. For general building structures, that may produce a better finish for if you're looking at an architectural wall. So joints and reinforcing are critical, I think, for helping to manage the crack. Several different types of joints, just generally grouped here: expansion joints, isolation joints, contraction joints, crack-inducing joints, and construction joints. Some, but not all, of the joint types listed affect load transfer. The ones that do affect load transfer should be coordinated with the design engineer of record to make sure that the design has accommodated that. So, isolation and expansion joints. Isolations in the upper right, expansion joints are in the lower left in this graphic. Isolation joints, both of these type joints, you have a physical separation to abutting pores. There's a physical distance provided between the joint. So your isolation joints allow movement in any direction. You can move longitudinally in the plane of the wall. You can move perpendicularly. In the perpendicular direction, they're not connected. There's no reinforcing bonded that crosses the joint. The expansion joint, physical separate placement, bonded reinforcing is discontinued at the joint, but there are slip dowels that are cast in that allow movement in the plane of the joint, but prevent relative rotation of the two sections of wall. The walls can rotate, but the dowels will help to make sure that you're looking at the wall working together as one unit. Contraction joints subdivide into full contraction joints, partial contraction joints. Full contraction joints are in the upper right. Partial contraction joints are in the lower left. Full contraction joints, all your bonded reinforcing is discontinuous. Slip dowels will allow linear movement along the plane of the wall to occur. But this joint cannot transfer any bending, so it needs to be coordinated if used with the design engineer. In the event that they designed that wall to be continuous across that point, this joint would not allow that to happen. Partial contraction joints, there is some reinforcing that crosses up to 50% is what we would consider as a partial contraction joint for 350. And water stops are shown in these walls, again, because these were developed for 350 type structures. Crack-inducing joints, these are most often, I think, seen in pavement design, where you have a formed groove or sawn groove or a tool joint at the surface, which reduces the section at that location with the goal of inducing a crack at that place. It works better in thinner members, not as well in thicker members. Many a time I've seen the sawn joint and the crack right adjacent to the crack doesn't always align with where you want it to go, even though you've weakened the section at that location. Monolithic construction joints, you still have two physically different placements. You've broken the pour, but there is no physical separation between the two abutting placements, and all of your bonded reinforcing is crossing the joint. So from a design perspective, you can transfer full load across that joint. But that joint doesn't have a lot of movement capability. You also want to make sure that you're going to place your concrete and cure your concrete so that you minimize the drying shrinkage, and wanted to touch briefly on unintended impacts of withheld water. If you trim water at the batch as you're batching, and that water is never added back into the truck, what is the final placed water cement ratio of what you have? Maybe your 0.40 water cement ratio, if you trimmed the water, now became a 0.38 or less, and you begin to risk early age cracking unintentionally by trying to go down that path. So just something to keep in mind. Also want to minimize cold joints if possible. So in summary, we design concrete assuming that it cracks. Everyone needs to understand that going into the project, and crack control requires responsibility from all in order to achieve the goals that are designed. We need to make sure that we specify the strength needed for the durability or serviceability needs of the project, and we also want to look at the importance that joints play in trying to achieve those goals. You need to make sure that you've designed and included proper reinforcing to accommodate thermal and shrinkage restraint.